basically anyway. So it's not a bad idea to just go ahead and factor everything. The mistake I noticed immediately on a few papers was, well, let's see, I'll show you. How do you factor the top? Shouldn't be too bad. How do you factor the top? With two numbers multiplying negative 14, it had to be 5. Positive 7, negative 2, right? How do I factor the bottom? What comes out? 3, so what would be left? 48 divided by 3. 16, and how do you factor x squared minus 16? Yeah, x minus 4, x plus 4. Now, one mistake I saw was a few people were saying the x-intercepts were negative 7, 2, 4, and negative 4. That's a little too far. Only 2 of those make this 0. The other 2 make it undefined, right? So x-intercepts are the x values that make it 0. What are the only x values that actually make this 0? Second? Yeah, negative 7 and 2. What does this tell you eventually? 4 and negative 4, what are those? Vertical asymptotes. Those are the x's I'm not allowed to use. So I got to put a wall there. So you can't use these. Right? So eventually that would be vertical asymptotes. And of course the y-intercept would just be this over this. In this case it'll be 7/24, which is roughly 0.28 or something. 0.3 or something, it's really tiny. Poor little dude, right? Make x 0, bam! Right, so getting this information, pretty straightforward. What about the horizontal asymptote? What situation are we in here? Yeah, the degrees are the same. So it's the ratio of those leading coefficients. So 1/3. Okay. And then the last thing we normally did when we did this is figure out the y-axis scale, because you have to get some more information before you know that. So right now I just know the y-intercept is really tiny. So let's see. This we should do by 2's maybe. Because you got to get out to 7. So negative 7, 0, and 2, 0 are my x-intercepts. My vertical asymptotes are at 4 and negative 4. I know my y-intercept is up here, right? So to be honest, I don't need any information because I know it's going to go like that, because what's it got to do at 2? It's got to go through. So since I know my y-intercept is up here somewhere, I know this is going to look like that. It's got to slam up against this, and then it's got to go through and slam up against that. But I don't know what's happening here for sure. So let's put in, if we put in 5, then I can get an idea what it's doing over here. Over here, I know it goes through there. That's good to know. So let's see what f of 5 is. So now that I know what I need to plug in, I can figure out what this is, and that'll tell me what this scale is going to be. So if I put a 5 in, I'm going to put it in way over there. I'm going to 12 times 3 over 3 times 1 times 9. See, the 3's cancel. 12 divided by 9, 3 goes into those, so that's about 4/3. It's about 1.3 roughly. Make that an approximate. What? You guys see how I figured out to put 5 in there? Most of you guys were helping me when we were doing that yesterday, telling me what's some good points. It's just because I don't have any information over here, right? So now I know it's at 1.3. So let's see. All my outputs are pretty small, yeah? I got a negative 0.3, a 0.3 there, I got a 1/3 asymptote, I got a 1.3. So let me make my scale maybe, I don't know. gonna get in trouble again probably. Let's do, why don't we do 0.3? Is that good enough, Jeff? Yeah, almost. Okay. 0.3, negative 0.6, negative 0.9, negative 1.2, Jeff. Yeah, good. You got it. Look at you go. So now we can put it there. Y-intercept, 0.3. So I know in here it goes like this. Whee! Horizontal asymptote, 1/3, which is about right there. I know f of 5 is 1.3. It's way up here. So I know up here is like that, because it's got to slam up against those walls, right? So once you put the walls in, it's just a matter of, is it up here or is it down there, right? And of course, over here, I know it's got to slam up against that wall, it's got to go through there, and it's got to slam up against that wall. So this is roughly the way I think yours should have looked like. I think, roughly like this. Roughly? Yeah, roughly the thing. Totally different function, but I think yours should have looked something like this. Okay. Did that help at all? I don't know. We've done a lot of those. Which part of that made the least sense? Does everybody understand why I have to do the Y scale last? Right? Because once I figure out this, it depends on how that comes out. That's going to tell me what my scale is going to be, so I can actually plot that point. Maybe. Okay. All right. Okay. Just to give you an idea, if you haven't started chapter 6 homework yet, you are behind, right? So if you're still doing chapter 5, you want to just kind of let it go, get into chapter 6, do sum of 6, right? I've got the practice test. Let me go ahead and give that to you, and then you just put it away. We'll talk about it next time, because when is the test? Next Wednesday, yeah. What's in this? 5-5 through 6-5. So just put this away for now. Unless you get really bored while I teach it, then you can just try it. Okay. Okay. Anything else from that quiz before we get back into? I've got a little outline for myself to remember what to cover. Because there's a very important thing we haven't really covered directly yet. There's a really, okay. What's pi represent? Real quick. We gave the letter pi, it's just a Greek letter. We gave that to a certain number. What's that number approximately? 3.14. And what is, and it goes forever, 3.14, 15, blah, 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 right? So every March 14th, 3.14159 at 159. Anyway, so back in 2015, Pi Day. You guys know about Pi Day? March 14th is Pi Day. So I was at a conference. Pi Day came on in 2015, so we called it Super Pi Day, and we had these little pies. And we're eating them, and we're all weird people. I know. It's just weird. It's just something we do, right? Join the cult. No. Okay. So Pi Day is there. So pi is obviously very important. What kind of applications does pi sort of come out of, or do we use it for? Say again? Circles. And in fact, real quick, if you take any circle, I don't care how small or how big, and you take the diameter, and the circumference. So if I took this guy's diameter and this guy's circumference, and I divided them, what freaked people out is they always got the same number, no matter how big or small the circle was. You with me? No matter how big the circle is, no matter how small the circle is, if you take its circumference and divide it by the diameter, you always get the same number. Are you guys semi with me? Did anybody know about this? No? Okay. All right, but do you understand what I'm saying? So one thing you could do with people is you could take something that's circular, you take a piece of string and you put it around the base of it, and you cut it right when it's around the whole base. That's the circumference then. So you can lay it out and measure it. And then you make a circle out of it and you measure across the diameter. And then you divide them and you get roughly 3.14 blah, blah, blah. You guys with me? I think the Egyptians estimated it to be 22/7 because civilizations noticed this. And some civilizations are like, oh, that's a number from the gods. Oh, shit, right? So, of course, we gave it a symbol because it's freaky. It's kind of freaky, no matter how big, right? What is 22 divided by 7? Does anybody got the calculator right there?
Three.
1, 4.
2, 8, 5, 7.
Blah, blah, blah. That's a pretty good approximation. Holy shit. So over the years, people tried to, by hand, come up with a better and better approximation of what pi is. And of course, now we can just make a supercomputer, just give me 5 billion digits of pi. Okay. Blah, blah, blah. All right. You guys all with me? You all know pi, but I'm sure some of that I just said was new to you, right? So that's why we give numbers symbols. Certain numbers get symbols because they come up in the weird places and they're kind of nifty. So there's another number that comes up, and there's two situations. I think I want to try to do this one first. Okay, well, now just stare upon that weirdness. Okay. What happens when x gets really big? Let's think about this. When x gets really big, what does this get closer and closer to?
0.
Does it ever get to 0? But what does the inside get closer to then? It gets closer to 1, yes? You guys with me? Because it would be 1 plus really, really tiny. It's getting smaller, so it's going to eventually get really, really, really close to 1. You with me? Does the inside ever equal 1? Hell no. Right? Because this never equals 0, it just gets close to it. What's happening to this guy? It's getting big. You with me? So what is 1 raised to any power? 1. But is this ever 1? No. So this is kind of weird. What will this come out to be? This is never 1, so the answer can't be 1, and this is getting stupid big. So it seems like maybe it just goes to infinity. It seems like it just keeps going. So let's try this out. You guys turned me the calculator back in, but that's right. Everybody who still has a calculator, help me out. In fact, let's do this. I'll show you this. I'll remind you about something. This will be good for you guys to see. I forget, is this computer? I don't think this computer has. No, okay. Too bad for me. Okay, if you don't have a calculator, don't worry, just sit and stare at this. There's the quiz. I see too many lamps, I think. And there. Oh, is it still turning on? There we go. Alright, so one thing I can do, I'm going to put in here 1 plus 1 divided by x to the x. So there's something we did a while back, and I want to show you. Actually, I can't even remember if I showed you this. I think I did. I've got a table that I could use, but I want to make sure it's set up correctly for me. So I'm going to go to table set right there above window, second window. So what I want to make sure is that it says ask right here. the independent variable is x, because y depends on what x we choose. So the independent variable, I'm saying, ask me what I want it to be, calculator, right? So when I go to the table now, it's going to be blank. Well, it should be blank. Dang it. Let me do some real quick. Do-do-do, do-do-do. All right, now it's blank. Okay. If yours is not blank, don't worry. You can just overwrite the stuff that's in there. So I want to let x get really, really, really big. So I'm going to choose some really big values. So for example, somebody give me a really big number.
24.
Say again?
24.
24? Is that what you said?
Yeah.
Okay. 24, sure. And what do I get already? 2.66. Anybody think there's a bigger number than 24? Anybody? Give me a number. Give me kind of a semi-big number. Anybody? What's happening today? Just tell me a number. Give me just a number. You can do it. Huh?
Million?
A million. Kick ass. Now we're talking. 1, 0, 0, 0, 0, 0, 0. 2.7183. Interesting. So let me just put in something crazy. I'm just going to put 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. It's going to be that forever. So if I step towards it slower, just put in there 100, 1,000, 10,000, 100,000. Do you see how the outputs are getting really close to something? Can you see that? As my inputs grow, the outputs seem to approach an asymptote. Maybe? Maybe? That's a little bit freaky because, again, I really want you guys to get this. This gets really close to 1, but this goes crazy. So if I raise something to a power and the power gets bigger, bigger, that's going to go to infinity. Right? 2 to the 100th power, 2 to the millionth power, that's just growing like crazy. If I raise 1 to any power, that's going to be 1. So the answer is somewhere between 1 and infinity. It just depends on who's growing faster or shrinking faster. So it kind of like evens out to be this number. Okay, now that to me is the less interesting example. That number right there, and you can't see all of it, but that is, let's do this. It would basically come out to be that. It's E, right? So if I let as x goes to infinity, this, let's call it y, goes to what we call E, which is about 2.7128, blah, 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 2.71828. I always forget that E. Blah, blah, blah. It's a little bit like 3.14, but it comes from a very different place. Okay, maybe. This, by the way, this function is related to compound growth of an investment. I am not a business person, but if you are a business person, you could be using this E for certain applications. A slightly more interesting place that this comes from is if I graph 1 over x. If I graph 1 over x, just the positive part. And I start at 1. And I say, how far do I have to go until this area there, do you guys see that? The area there is 1. And the answer is this number. If I go from 1 to E, the area under this is 1. Okay, that's a little weird for us. We're not used to thinking about area under a function and all that kind of business. That's actually calculus. But we don't have to understand how to get it. We just have to understand that there's an area there for sure, right? Calculus actually helps us calculate what that area is. So there are 2 places where this same number comes up. So of course we gave it a letter. Now here's something. The dude that gave this the letter E is Euler. I don't know if you guys remember a while back I wore a shirt, Euler's Identity. I can't remember if I wore it for you guys or just for my other class. Euler, E-U-L-E-R, Euler. He didn't give it the letter E because his name starts with E. He was just giving different letters to different things, and when he got to this number, he was on E, which is kind of funny. Okay, I like it. Maybe. Okay, all weird shit. So if you didn't quite grasp any of what I just said, hopefully you understand this number came out of two very different seeming applications. So of course we gave it a letter. Now, something even more interesting about E. So if I do this and I do this, right? Real quick. Y equals 2 to the x. What do you get for y equals 2 to the x if we do that here? We'll do it in purple, and then we'll do the other one in red. Shit, I like it. 2 to the x. What's 2 to the 0 power? 1. What's 2 to the first power? 2. 2 to the negative 1 power? 1/2, right? 2 to the negative 1 is 1/2, flip it. So you get, of course, this standard picture we're used to by now, hopefully. That's any exponential. If I do this one, 3 to the 0 is still 1. 3 to the first is 3. 3 to the negative 1 is 1/3. Oh, scheisse. Okay. All right. Neither one of these bases accurately portray growth. Do you understand how this is growth of something? You throw a couple of rabbits in a room, you give them some food, and over time they're going to grow a population of rabbits. Yes? Don't think about what that means, but anyway. And their growth is going to look like this, but it's the in-between guy. The e to the x is going to be in between these two because it's in between 2 and 3. So when I look at this function, it's better to model population growth. And the reason that is, if I have a population that's growing by 13% over time, are you guys with me? Then the model for it would be the beginning population e to the 0.13t. I can actually see the 13% growth in there. So again, that's another reason E is important. It makes a good base for a growth function, because then I can see the growth rate. Okay, maybe. All weird shit. All of this is just to tell you E is a special number. That's why we gave it the letter E. We gave it a symbol. We didn't give it a Greek symbol just because. Okay, now, let's see if you guys remember this. What is can anybody tell me the inverse of this? We created it together. We graphed it first. We didn't even know what it was, and we graphed it. What is the inverse of 2 to the x? Remember, we graphed 2 to the x, and then we graphed the inverse. What did we end up giving this the symbol of? Log. Yeah, so the inverse, so this is f of x. The inverse is log base 2 of x. Right? And that's why, if I ask you a question like this, why is that question easy? Do you guys remember? What do these do to each other? Because they are inverses. So that's why this answer is 7. That's easy as shit. Let me do this. What about this? What's 3 to the log base 3 of w? What do these do to each other? 3 to the x in log base 3 of x. What are they? What's their relationship? They are inverses. What will they do to each other? What do inverse functions do to each other?
Kill each other.
Kill each other. Bam, the answer's W. Done. It's exactly like me saying, what's the cube root of 7 cubed? It's freaking 7, Jeff. All right, well, what's the cube root of 7 cubed? That's still 7 that kills each other no matter which way you put it. No matter which way you put it, they're going to kill each other because they're inverses. Maybe. Yes? Oh, thank you. It's just watching a blank calculator screen. Boom, 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 boom. Boom, 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 boom. Okay. Okay. So this is why I like to do it this way. We talk about this, we talk about the graphs, and then we immediately do the inverse graph before we even know what the function is. And then we give it a name, and unfortunately, we weren't around when they chose the name of the inverse, because that's kind of silly, but oh well, too bad for us. Calling a function log. What the hell was going on? What were they drinking is my question. Okay. Maybe. Oh, okay. So for example, real quick, the square root of 2, if somebody else would have suggested it, we could have used that to mean square root, right? That could have been the symbol instead of this. Are you guys with me? So that's the symbol we chose. It could have been better, but oh well. We're used to it now. We can't change it. Okay. I don't know. Maybe. So let's do this. Okay. So now we got this new base, E. What is its inverse? So I'm going to write something up here, and I'm never going to write it again. So if I have f of x equals e to the x, what is its inverse? Right, so remember, what was it for 2 of 2 to the x? If f of x is 2 to the x, what's the inverse? What was the inverse? We just had it up here. Log base 2 of x. So f of x equals e to the x, what's the inverse? That is something I will never write again. It hurts me to write that, weirdly enough. Does anyone know what the actual, we don't use this symbol. We use a different symbol. Natural log. ln, we use the natural log. All natural log means is log base e. It's just the symbol we chose to use. Okay, maybe. Okay, so something like, for example, what's natural log e squared? Okay, you can do that if you need to. How do natural log and e relate? They are inverses of each other. So what are they going to do to each other? Cancel each other, right? What is e to the ln x? X. What do e and ln to e to the power ln of something do to each other? Kill each other. It's x. Whatever ln does, e to that undoes it, because they are inverses of each other, just like adding 3 and then subtracting 3, right? And maybe. Okay. So it's just another log, it's just another base, it's just, e is just a special number, right? Okay. So that's one thing. Remind me, can you guys tell me anything about the graph? I'm not going to tell you what that base is, but can you tell me anything about the graph of this? Can you tell me the shape of it? Yeah, do it again. Yeah, so I know the shape is like this. What happens at the x-axis. What's the x-axis? What does the x-axis act as? What does it have to do if I let x get really small? What's it got to do? It's close to this, so there's an asymptote there. And this, of course, is always 0, 1. Because when I raise anything to the 0 power, I go 1. Okay, I like it. So that looks like this. So tell me this. What is the range of this? Not all real numbers, because the range is all the outputs. What outputs do I definitely not get? I don't get any whats. I can't get 0 or negative, so I can only get, well, no, I can also get 0.35, I can get 1.769. So what's the lowest thing I can almost get? 0, but I can't get 0, right? And what's the highest thing I can get? Infinity. Okay, so there's the range. And what's the domain? Yeah, all real numbers. I can use any number, I can plug any number in there that I want to. Right? It goes forever. So that's negative infinity to infinity. Now let's look at the log. The log. So where does the asymptote go when I reflect things? The y-axis. And of course it looks like this. And it goes to the point 1, 0. That makes sense. Since that always goes through 0, 1, that always goes through 1, 0. So what's the domain of this guy? Can I put a 0 in? Can I put negatives in? What's the domain? From, yes, to infinity. You see how the range of this became the domain of this? That's how inverses work. Every y changes with every x. So the whole domain changes with the range, right? So what's the range going to be? Well, you can look at it. Right? This goes forever down, this goes forever up. So what's the range? This goes forever down, that goes forever up. What's the range? Negative infinity to infinity. See how that was the domain? Now it's the range, right? That's how inverse functions work. All the x's and y's switch. So the domain and range switch. So, all right. You're going to be excited about this, I know. That's some basic stuff. So you got to know the look of it. You got to know where the asymptote is for both of these. So what's going to happen with do you see a transformation? What's the transformation here? Left one. I love it. So again, transformations don't give a shit what the function is. When I see an x plus 1 in some function, I know it's going to go back 1. It's going to go left 1. So a normal log base 2 has an asymptote here. It goes through 1, 0. Right? So the normal log base 2 of x. What's log base 2 of 1? 0. What's log base 2 of 2? What's log base 2 of 2? What power does 2 need to become 2? 1. So it goes to the point 2, 1. And what about 1/2? What's log base 2 of 1/2? What power do you need on 2 to make it become 1/2? What power makes something flip? Negative 1. Okay. So at 1/2, it's negative 1. there's this, there's the base function. And what am I gonna do with each of those points now? I'm gonna just move them left one. So I'm gonna take this guy back one, this guy back one, this guy back one. And then what happens to the asymptote? It was here, where is it now? It goes back one, right? So now it's gonna look like this. I just took that and moved it back one. So all the old transforms, as we learn new functions, we'll do some transforms with them. The transforms work the same exact way. So if I put like a negative x in here, that would just make it flip, right? Reflection, just like before. So all the transformations are the same, thankfully. Okay, I like it. Now let me ask you this. All right, let's do something very direct here. Can you guys? So let's do. Let's remember something. How do I find the domain of this? How do I find the domain of this? What has to be true for this? It can't be negative. So the inside has to be what?
Either or equals 0.
Yeah, it must be positive. Must be greater than or equal to 0. Positive or 0. So the inside has to be at least 0. So then if I solve that, right, negative 1 divided by 2, I get the domain. Are you with me? That's how we find the domain for any function somebody gives me. I say in English what has to happen, and then I'll write down what I just said in Mathish. Right, so the inside of a square root has to be not negative, it has to be 0 positive. So the inside has to be at least 0. Bam! And solve it. So what about a logarithm? So the basic log, oh crap, red's gonna die. Give me a purple. So the basic logarithm has an asymptote here, goes through there, right? So the basic logarithm's domain is greater than 0, right? Meaning the inside has to be greater than 0. So if I said, what is this guy's domain? What's got to be true about this? Yeah, I can't handle 0 as an input. I can't handle negative numbers as an input. So the inside has to be greater than 0. See how it's sort of like a square root? But a square root's allowed to equal 0, whereas a log can't handle 0. So x has to be just greater than negative 1/2. So this would be like this. This would be like that. I can't include negative 1/2 there because there's an asymptote right at 0. So that should feel very familiar. We've done finding domains before. Now I just have to memorize that for logarithms, they can only handle positive inputs. So the inside must be positive. And then you just solve for x. Not a crazy big deal. Very similar to what we've done. So logarithms, be really careful. Logs and roots are not the same. They're so not the same. But they are very similar. Okay. And then, finally, I don't think I gave, no. Yeah, I did. I gave you the property of logs handout, right? Yeah, this guy. So we talked about each of these properties last time. Right, so the product rule, this guy, I kind of proved it to you. And then the quotient rule, we sort of did that based on what we did up here. And then, of course, the power rule is the big one. So if you look at a few of these, how can I rewrite this using this product rule? What would that look like? How can I rewrite this? So how does the product work? How could I rewrite that? So the log of the product of things is the sum of the log of each piece. And yesterday we actually proved that. So how can I rewrite this? Log base 3 of 3 plus. And what is log base 3 of 3? What power does 3 need to become 3? 1. So this is 1 plus log base 3 of x. That should feel a little bit like simplifying radicals, where you break it up into a part you can do and a part you can't do. Right? So I broke it up to a part I can do, bam, and a part I can't do, bam. What about this guy? So now I'm doing it backwards, right? I can rewrite this as a single logarithm. Log base 12 of what? 3 times 4, yeah. And of course, log base 12 of 12 is 1. Okay. And the same thing here. What does this become? Log base 4 of? Yeah, 1/3 of 12. 1/3 times 12, 4. So again, that's 1. Okay. Very creative with this worksheet. Okay. So how can I rewrite now? I've got a quotient. So it kind of makes sense. When I multiply things, I can write it as the sum of the logs. When I divide things, I can write it as the difference of the logs. There's a nice symmetry there, nice analogy. So how would I rewrite this? Log base 3 of 3 minus, yeah, what's log base 3 of 3? 1. Log base 3 of 5, I don't know what it is, so there you go. I do the part I can, and I leave the part I can't. So here's where the real power of it shines through. I don't have a clue what log base 5 of 75 is. I don't have a clue what log base 5 of 3 is. But I am taking the difference, so I can rewrite that as a single logarithm. What goes inside? 75 divided by 3. And what is 75 divided by 3? 25. And what's log base 5 of 25? Because 5 squared is 25. I love it. Now, one thing I haven't mentioned, what's kind of weird about number 3? Yeah, so like if I said to somebody 4th root of something, you break it up into 4 parts, right? And cube root of something, you break it up into 3 parts. And then I put this symbol down. And they're just learning radicals. So they're going to go, wait a minute, what is this? Well, what is this? What is this? What's understood to be here? A 2. A 2 is just understood to be there. Why do we do that? Because it's the most often used one. So we want to make it real quick to write because we use it all the time. So we just don't write the 2. What do you think the most commonly used log is? Considering our number system, yeah. Right. So when you see a log without a base, it's log 10, which is called the common log. So log base 10. So when you look at your calculator and you see a button that says log, that is log base 10. So you can do this 2 different ways. If I do this using the quotient rule, how can I rewrite this? Log 1 minus log 10. 10 to what power is 1? 0 power. 10 to what power is 10? 0 minus 1 is -1. Now, what's a quick way to see that? The base is 10. What power does 10 need to become 1/10? -1. I get the same answer just more directly. Because I can just see, I just got to flip it. So I just have to have a -1 power. Okay. And then finally, real quick, this one is the nicest one. If you have log of something to a power, the power can just come outside. It's that simple. So what's wrong with this one? Why is that not in the right form?
Because it's the square root.
Yeah, what is the square root? What's a better way to write square root?
X to the 1 half.
And then what can come out front?
1 half.
The power. I love it. Kabam. So if you have something written as a root, just rewrite it as a power. What about this guy? Do I have to do that? What can come out? What can come down? Square root of r. Yeah. The power is square root of r, so I just can take the whole thing down. That's what that property says. And again, we proved it yesterday, right? And of course, I forgot to turn my camera on. Everybody at home, sorry. Okay, so let me kind of scan this real quick. Okay. So those are those properties we talked about last time. Okay, maybe. All right, I think that's about enough. So, Tuesday, review day. I'll have the answer key for the practice test. The quiz is graded. And then Wednesday, of course, is the test. So come ready with questions